So this is the second session on the topic music through MATLAB, and what we are going to do in this session is to see how a simple musical note can be generated through a computer program. I am of course going to assume some simple mathematical background on the part of the viewer, and also that he knows a little bit of programming. But even if you do not know MATLAB, it's okay. Once you understand the concepts, you will be able to implement this in other language as well. Alright, so first we start by trying to understand what is a musical note, and then we will see how to generate it. Alright, so what is a musical note? It's basically a periodic signal of specific frequency and duration. So in order to get some ideas about the kind of frequencies we are dealing with, look at the frequency which corresponds to the middle C on the piano is about 261 Hertz. Of course, different musical notes will have different frequencies, but this gives you some idea about the frequency. Then typical duration is 0.4 seconds. Again, different notes in a melody can have different durations. For example, this could be as small as 0.1 second or as large as 2 seconds or even more. However, these values gives you some idea of the numerical values involved. Alright. Now the quality of the musical note can be controlled by two things. One we call as the wave shape, and the second we call as the envelope shape. So in order to understand this easily, let us look at the graph of the musical note. Now if you look at this graph, on the x-axis we have plotted time, and you can see it starts from 0 and goes up to 1 second. So the note that is generated is of 1 second duration. On the y-axis we have plotted the instantaneous amplitude, and you can see in this case that the nature of the waveform is triangular. Actually, I have kept the frequency of this waveform deliberately small so that you are able to see the waveform, and different waveforms will give you different quality of sound. In this case this is triangular, but you can have square wave, you can have a sine wave, you can have a sawtooth wave, and they will produce different timbre. Alright. The other thing that decides the nature of the musical note is the amplitude variation. So you can see it is jumping to a high value, dips a little, sustains, etc. So in order to see this clearly, let me show you the next graph. So here I have actually used the frequency corresponding to the musical note, and since that is generally large, of the order of 260 Hertz and so on, so that time period is quite small compared with 1 second. That is why you don't see the waveform. However, when you plot the waveform in this fashion, you are now able to see how the amplitude changes. So initially it changes fast, what is called as attack. It increases fast, then decreases a little, then the phase which is called as sustain. So sustain does not necessarily mean that it's absolutely constant. It is decreasing in this fashion for this particular note, but the rate of decrease will depend on the nature of the note that you are trying to generate. For example, if it's a sitar note, this will die faster, but if it's a note generated by a flute, this would be relatively constant, and finally it comes down to 0, so that is called as release. So you got attack, A, decay, D, attack, decay, sustain, and release. These are the 4 phases of the ADSR, and different envelopes will produce different effects. So you may have a ADSR which is sustain type, or it may be dying type, as we have just now discussed. Alright, with that background, we are now going to study the generation of a simple musical note. The simplest that you can generate is that of a sine wave. So what is the equation? As all of us know, x is equal to a sine of 2 pi ft, where f is the frequency, and this t, which is the time period, is reciprocal of the frequency. So what we do in the program is that for various values of t, we generate values of x. So large number of samples are generated for different times and they are stored. So what are these values for time? So you can start with t equal to 0, so you will get some value, say x1, then t equal to ts, you will get some other value, say x2, and so on, right up to the time where t corresponds to td, where td is the duration of the note. Now what is this ts? Ts is called as the sampling time and its reciprocal is called as the sampling frequency. So the question now we ask is, what should this ts be? So ts should be small compared with the time period of the sine wave. How small? So we'll take a couple of examples. First we assume that this sampling time ts is 10 times as small compared with t. Plot the sine wave and see how it looks like. So choice of ts. So let's assume f equal to 250 Hertz. In that case t is equal to 4 milliseconds and ts we assume is 1/10 of t. And since sampling frequency is reciprocal of this, clearly sampling frequency is 10 times the frequency of the sine wave. With this, if we plot the sine wave, it looks something like this. So again we have plotted time on the x-axis and instantaneous amplitude here. So even though this is the sampling frequency is 10 times the frequency of the sine wave, even then you see that the nature of the sine wave is not too great, because in one cycle basically you have 10 samples. You can see this in a clearer way if you plot the waveform. Instead of plotting it this way, you can plot it as a line diagram. So this is the first sample, second, third, fourth, fifth, sixth, 7, 8, 9, 10, and then repeat. So you got 10 samples in a time period, but you do not get a very great sine wave. If we want to improve this, we need to increase the sampling frequency. That is what we need to do. So one typical value that is used is 22050. This is one of the standard sampling frequencies, although you have much higher frequencies also which are used, but right now we are going to use this frequency. So if this sampling frequency is used, you will see that the waveform that you get is much closer to the ideal sine wave. And this is another way of plotting it, as we have seen just now. Alright, so now we would like to write a program to generate a sine wave. But before we do that, let us try to understand these terms which we call a stored waveform and how it is converted into sound. So when you execute a statement x equal to sine 2 pi ft, after defining t having various values, you will be generating all sample values for x. So at this time it is just stored in the computer and doesn't produce any sound. But when sound command is executed, all these samples are sent to the sound card. So that command is sound x. What is sent? X, which contains all the samples for various values of time, and that is sent to the sound card at this rate 22050, because this is the rate at which we generated. So this is the rate at which we send, and therefore our duration calibration will remain correct. So this command, as I said, will send x to sound card at the sampling rate of 22050 samples per second, and we use the same fs so that the calibration for duration of the note is not disturbed. Okay, so let us now look at the little code in MATLAB which will generate this. So CLC is simply clear console. Clear, this clears all the previously defined variables. Now we define duration of the note as d equal to 1, and as we have seen, it is calibrated in terms of seconds. So d is equal to 1 will mean that you will generate a note of 1 second duration. Then you generate the t vector. So in MATLAB it's easily done. So t equal to 0, it starts with 0. Then the next value will be 1 upon 22050. Remember, this is ts, the sampling time. Next to that will be 2 upon 22050, 2 times ts, etc., until you reach the duration of the note, which is d. Then you define f equal to 260. This could be something else also. Then you generate your sine wave. x equal to sine of 2 pi ft, and then send it to the sound card. Incidentally, you can also store this sound vector in a file. So first you define the file name. So all this initial portion of this statement you can see on the right hand side is just the path for the MATLAB, but this is the name of the node that you are storing, simple node dot wave. So the sound file is being stored in the wave format, note that. Then you write audio write file name x to 22050. So what you are doing, you are generating this wave file which contains all the samples of x, and then you specify the sampling frequency at which it was generated. Then you plot t and x, but in this case we are plotting only 500 samples so that the waveform is clearly seen. Otherwise, if you use the entire duration, all the samples, then we have already seen that you will hardly be able to see the waveform. I have talked about the path here. So path for the file name in your computer can be different, so you have to take care of that. So this is the waveform that is plotted by this command, plot t. So 500 samples of time and the same number of samples of x are plotted, and you can see that this is sine wave. So let's see how it sounds. So let's play this. Let me play it again. And you can see that there is a little click at the end, and that is because you don't know when the sine wave ends, because sine wave may be having some value itself, but then it suddenly comes to 0, so that causes a click. And we can remove this by using the envelope. So the correct envelope is of course the ADSR, but what we are going to do is to generate an envelope which is mathematically simple to do for this particular session, and later on we will see how to write the program to generate ADSR properly. So right now the kind of envelope that we are generating is just a half sine wave. So that is for the entire duration of the note. So here of course this is quite different than ADSR. Nevertheless, it is an envelope. So it increases, reaches a maximum, and it decreases. So how to generate this? So you have a simple equation, E equal to sine of pi t by d. T is the vector, remember, it will have values like t equal to 0, ts, etc. And when t is equal to d, this parameter within the brackets is the angle that reaches pi radians. So therefore when t is equal to d, duration in this case is 1 second, it completes 1 half cycle. So this is the envelope. But now what you have to do, in order to get the complete musical note, you have to multiply the original x with the envelope. So you generate the musical note y, which is a point by point product of x and e. Remember, the number of samples in t is same as the number of samples in e, and that is also same as the number of samples in x. So the corresponding point by point multiplication is done. That means x1 will be multiplied with e1, x2 will be multiplied with e2, and so on. That is why you have to write point star in MATLAB. Otherwise it will try to do matrix multiplication. So it is important to remember that you do point-wise multiplication. Alright. So let us see the program for this. Again, most of the lines are similar, except that we have now generated the envelope, sine of pi t by d, then multiply the two and send it to the sound card. Again you can store it in the file. So let us see how it sounds now. You can see that the click is removed, and this is the entire waveform when x is multiplied with the envelope. So in this particular session we have seen how to generate a simple musical note, how to store it, and how to play it. In our next session we shall see what is the musical scale, how to generate other frequencies, and how to generate a melody. And in later sessions we will see how to generate ADSR, how to generate different waveforms so as to get different timbre of sound. That's all in this particular session.